So much for coming to my Science on Tap Talk. I really appreciate it. So without further ado, I'm going to jump in and tell you about the new tool that I'm building to map entire galaxies. And as Megan said in her wonderful introduction, I love coming back to Santa Cruz to give a Science on Tap, even if it's virtually, because this is really it's so fun and nostalgic. So jumping straight in. Really? You're just gonna beep at me? Cool. No. Okay, we can do that. Okay, great. That is perfect. So now a brief outline of my talk. I'm going to go into a bit of introduction about what spectroscopy is, and then I'll talk about a couple different kinds of spectroscopy, long slit versus integral field. Then I'll tell you all about my instrument, and I'll jump into future science that we'll be able to do with it. So as I think everyone knows, astronomy really is the study of light primarily. Most of the things we look at, we study via light coming in through some sort of collecting instrument, generally a telescope, where we focus the light with a primary mirror, and a secondary mirror helps us to focus it further down to its perfect focal point where an instrument will receive it and then hopefully do interesting science with it. And the main idea with that is that white light, which is what we generally are collecting of the whole spectrum of light, is made up of all of the colors. And Pink Floyd is really fantastic at making this popular, although he didn't get the angles quite right, but by passing white light through a prism, it separates it or disperses it into all of the colors that we can see. And nature is also already really an expert at dispersing light into all its colors. So when we disperse light like this, we generally have a white light source, and we'll narrow what we're looking at just down to a slit or something like that because it makes it easier to study. Then we'll pass it through a prism or something else that disperses the light. And with a simple white light source like that, we'll get a continuous spectrum or a rainbow. And so if we looked at just the core of what was coming from the sun, we would see a continuous spectrum like this. If we look at not just a white light source, but say heated gas of one specific element, when we disperse the light here, we'll actually see bright lines that characterize the gas. So for example, we're very used to this we call them neon tubes, but there can be many different kinds of gas in them. By heating that gas, usually by running electricity through it, we can get it to glow a color, as the tube here shows here over on the left. And then when we disperse the light out, we'll get distinct emission lines that when added together form that light. So by dispersing it into its component colors, we're actually able to learn a lot about the gas, in fact. So with emission lines, we get them because the gas is in a higher energy state. So like a child very high on candy, say, since we just passed Halloween a bit ago. And then when the electron drops to a lower energy state, it will let out a photon, and then the electron will stay down there at the lower energy state, like a child sleeping. Then if you took that same gas, but you had it cold in front of the white light source, we see actually that same set of lines, but they show up as dark lines because they are absorbing the photons at that specific set of wavelengths. So as a demonstration again, so during absorption, you'll take, basically you've got white light coming through here, and it hits the electron at that lower energy state, like a child sleeping again. So once it hits, it will absorb that energy and jump up to a higher energy state. And so that means that there are specific portions of the spectrum missing, just like a very enthusiastic child. So in fact, when we're talking about the sun, I said the spectrum coming from the core of the sun would be a continuous spectrum, but the outer layers of the sun are actually cooler than the core. So the sun's atmosphere's cooler outer layers absorb certain wavelengths of light, which leaves us with an absorption spectrum like this, with all those dark spots. And so to expand it into quite a bit more glory, this is what it looks like. In fact, it's really incredible. And all those lines tell us about different atomic elements that are in the sun's atmosphere. And so the cool part is that since each element has a unique atomic structure, whether it's carbon with its 6 electrons in a unique structure on the outside, and sodium with, I never remember how many electrons there, in fact, when we have, since they all have unique atomic structures, they each have a unique set of colors or a fingerprint of colors that will define exactly the presence of the carbon or the sodium or whatever atomic element in that gas. So it's really similar, if you want to think about it, to barcodes, using barcodes as unique identifiers. When you scan the barcode on the left, you get my favorite Honeycrisp apple, but when you scan the barcode on the right, you get a navel orange. So, but those barcodes uniquely identify to a checkout stand exactly what produce you're purchasing. Or any, not just produce, I guess. So we're used to really thinking about the periodic table of elements like this to uniquely identify all of them and, you know, supply important information. Astronomers really look at the periodic table closer to this. So each element will just have a very, you know, if you just go down the column, a very different set of lines, either in quantity or in position, which tells us exactly what elements are present and generally to what extent, how much, at least relatively. So when we look at our sun's absorption spectrum, we can start to decode some of these like really thick lines because they're easy to identify. So for example, this red line and these set of blue and sort of teal lines show us that there's a lot of hydrogen present in our sun. These 2 orange lines are from sodium, and this band of 3 green lines are from magnesium. So there's tons of other lines present, meaning there are lots of other elements present in the gas, and so all those elements will generate all the many lines. But astronomers are still studying the sun to decode everything that's present in its atmosphere and to what extent. So it's a really great tool to have right near us to learn to do all this. And as much as I love the beautiful color plots, as a scientist, we don't really look at our spectra specifically that way, our solar spectra. We generally look at them as a graph with brightness on the y-axis and wavelength or color along the x-axis. And I've color-coded this bit here in the middle to remind you what we're looking at. But we see those absorption lines or dark spots as big dips in the brightness. And so, you know, you can still see those blue and that red line that showed hydrogen, the orange lines here that are sodium, and the sort of the sequence of 3 green magnesium lines there. So we're really used to looking at them as plots. So as a reminder, the emission and absorption lines are unique patterns that identify the elements that are present in the gas. And they're really useful to astronomers. Don't remember why this is here. I guess I wanted to transition. That's right. So this is what our sun looks like. What do the spectra of other stars look like? So specifically to get the spectrum of a star, we'll use the telescope to focus the light into our instrument, as I mentioned before. So here's Vega, for example, shockingly bright. And we block as much of the background light with a mask or like this, for example, to form a long slit, because the more other objects we have, the more contaminated our spectrum will be. So if you want to just look at the star, clearly you just want the star's light. So in this case, it'd probably be an even narrower long slit to try to block out some of all these extra stars. And then you disperse the light. So when you disperse the light from Vega, for example, again with our brightness on the y-axis and color or wavelength along the x-axis, we see a series of absorption lines which clearly show the presence of hydrogen. Excellent. And if the star was moving with respect to us, we'd be able to tell the velocity. So putting a long slit across our object and dispersing the light is called long slit spectroscopy. And it's a really useful tool in astronomy. So, okay, we've only dispersed stars. What about long slit spectroscopy of other astronomical objects? So we can do long slit spectroscopy of Saturn, for example. So if we take Saturn and mask it, it's really a shame to cover up that whole picture because parts outside the mask are beautiful. So what astronomers normally do is we put a band across showing where we actually took the light from, because that puts the rest of it in context. So if I show a smaller picture of Saturn over here with the presence of where the long slit is shown by this green line, when we disperse the light out to the spectrum, we're getting all the wavelength information in the x-axis, so you can sort of see by the change in the colors here. But we're also getting all of the spatial information along the slit. So for example, we're getting light from the ring, the disk of Saturn, and then the other side of the ring. So this is really powerful because we're getting spatial information as well as the wavelength information, which can let us to start learn things about what Saturn's up to. So to zoom out a little, this is the whole spectrum that we're getting. And I told you before, we don't generally color code it. So when we stop being limited by what our eyes can see, this is what our detectors actually see. So you can see there are parts in the red spectrum that our eyes aren't sensitive to, but our detectors do just fine seeing that. So then if I extract light from the ring of Saturn here in blue and from the disk in red, it will look like this. So again, the ring is blue and the disk is red. These spectra look pretty similar, but they're not quite the same. So they're similar in the sense that they've got magnesium lines, sodium lines, and hydrogen lines. And if you remember, I was talking a lot about the sun. That means it's showing that Saturn's rings and disk are lit up with reflected sunlight. So that's primarily the way we can see the planets around us. In fact, it's reflected sunlight. But there are some differences here. There's this giant set of absorption lines here. So the really cool part about that is that's actually absorption from light in Saturn's atmosphere. So as the light went partly through into Saturn's atmosphere in the disk, it made it partway in and was absorbed and eventually was reflected back out again. So the light has been absorbed as it came in and out, meaning that we can tell what Saturn's atmosphere is partially made of. So in this case, it's methane in Saturn's atmosphere. So that's really cool. We didn't have to go to Saturn to know what one of the primary components of Saturn's atmosphere is. Awesome.
Rosalie, can I ask you a quick question?
Yeah, definitely, please.
So I'm sorry, this is a newbie question here. So if the cloud absorbs the light but then reflects it back out, I would think that we would see the methane in the spectrum, but instead there's a dip. Can you just explain the I'm thinking it should be positive and it's actually negative.
Yeah, it should be, it's negative in the case because basically you have electrons that are chilling at their lowest level and the light came by and that electron was like, hey, look at that delicious light that is exactly the right wavelength for me. I'm going to take it out of the spectrum. So the electrons grab the photons that they like the best and absorb them, and then they keep them.
And they don't drop back down and then release a photon of the same wavelength?
Not on any time scale. So they're actually using it to warm themselves. So they take that photon and that slightly higher energy that an electron now has, and it's transmitted to other atoms through collisions instead of being emitted back out. That's a great question.
Thank you.
That's just a function of the density of the atmosphere there. They're having collisions more frequently than than the time scale that they emit the light back out. So that's an excellent question. Awesome. Any more?
Not for me anyway.
Okay, thanks, Ron. So then we can jump into, okay, that was a solar system object. What about galaxies? So I'll pick my favorite, well, not my favorite, I'll pick a galaxy here, UGC 2936. The name is pretty silly, but you know, on the scale of what we were talking about, this is about 2,000 light years for that little bar right there. So he is, you know, a good size and, you know, sort of far away. And if we put a long slit on him, I'll show it here just outlined in yellow, because if we cover him up, there will be nothing sticking out on either side. So when I grab the light from them, again, okay, I didn't put lines here, silly me. We've got the light in the continuum coming from the core of the galaxy here, and then we've also got light coming from the two arms of the galaxy above and below. So I'm sort of trying to tell this with the galaxy radius on the y-axis. But But then we're noticing something interesting on the x-axis. We're not just getting one wavelength for hydrogen in these nitrogen lines. We're actually seeing a really distinct structure. So that's cool. The galaxy has emission lines, but why do the wavelengths change? So I have a video that will hopefully help explain that. But briefly, this is the Doppler effect. So it's the change in wavelength or frequency of a wave, which light is, for an observer that's moving relative to the source of the wave. So for example, if the light bulb is moving towards this lady in blue, she'll see the wavelengths of light compressing, meaning it will look more blue to her, whereas this lady in red is seeing the light moving further from her, so the light is actually stretching, so she will see it more red or red shifted. So I'll let the video try to say it, so you've heard it at least in a few different ways. Video go.
Blue light has shorter wavelengths than red light. When an object in space moves towards us, its light waves are compressed into higher frequencies or shorter wavelengths, and hence we say that the light is blue shifted. When an object moves away from us, its light waves are stretched into lower frequencies or longer wavelengths, and we say that the light is red shifted.
Hopefully you all will forgive me for the completely silly video, but I really love how it demonstrates, you know, as you're moving away from Earth, as objects are generally moving away from Earth, you'll see the light be red shifted. So this,
blue light.
This is the one that shows it a little more calmly. So as the light source starts here, you can see it's making just perfect circles of light at the same pattern, but as it starts to move, all the waves start to be bunched on this side, so it would be blue shifted, and stretched on this side, so it would show up as red shifted. So hopefully, when I start talking about how they're red shifted, it means the wavelengths are being stretched, so we can actually use that to tell motion, direction. Same with being blue shifted. So then this cat actually shows us really nicely what's happening with the galaxy itself. Right? Because we saw some of the wavelengths. Let me just jump back, which means that video is going to go again. Oh no. Some of the light, if we take the center of the galaxy as, you know, our reference, some of the light is at longer wavelengths or redshifted. Oops, wasn't supposed to say that. And some of the light is at more blue wavelengths. So if I jump through the Doomful video, the cat shows us that, you know, this end of the cat is always coming towards us, and would look more blue to us, and that end of the cat is always red or going away from us. So with the galaxy specifically, again, if we're using the center of the galaxy as a reference for our line, the side that's coming towards us would appear more blue or blue shifted, and the side that's going away would be red shifted. So then for this galaxy, we can use that red shifted and blue shifted information to say that this side of the galaxy is rotating towards us, towards you, and the top side is rotating away. So the galaxy is doing this in space. And that's really cool because we would never have known that otherwise. So this kind of information from these lines both tell us what's present. We know there's hydrogen and nitrogen in the galaxy, in the gas, but we also know we can use it to start understanding how the galaxy is actually rotating or moving overall. So this is really powerful. These long slits can reveal the lines and their structure. However, they can also really miss the bigger picture for big structure scale. So for example, if I put a long slit across these objects, really there's so much left that we don't know what happened. So if we were going to observe these objects with, say, this galaxy in the bottom right with this long slit multiple times, but we wanted to see the whole scale, we take 1 hour exposure here, another hour exposure there, another hour exposure there, and so on till we had a much bigger picture. So that just got abruptly very expensive in terms of telescope time. That would actually be, on average, a whole night, because we didn't even talk about any calibrations in there. So, or if we wanted to do it for Saturn, it would probably take another whole night. So with these long slits, we really miss the big scale structure. And so if people can post in the chat, I'll try to look at it. What do you guys think from this picture where I only give you 4 slits of information? What do you think is present in there? Anybody want to type or turn the microphone and jump in?
A starry night.
Yeah, you guys got it. You're aces. Not everyone gets that one. So awesome. So here's a movie poster, if it will let me go. Yep, there it is. You guys guessed it just perfectly. So here's a movie poster from a few years ago. Any guesses from what this movie might be? Just from 4 slices of information? It's okay if you guess wrong. Wonder Woman, someone got it. You guys are aces. I really like this poster of Wonder Woman because she's red shifted on one side and blue shifted on the other. I'm such a nerd. But I'm so happy you guys got it. So really the lifelong challenge is trying to tell from, 4 pieces of information or 5 pieces of information what's going on with the whole system. So for example, these folks that are blindfolded are trying to, get the idea of what an elephant looks like, and they're going to come up with really different results based on what they saw, whether it's a tree, a hose, a spear, a fan, a wall, a rope. Based on where they looked, they found really different pieces of the big picture. So getting the whole picture is important. Several people have asked when I've given this talk in the past, so I now have a slide on it, what happens if you take the entire galaxy and you just disperse the light? You don't bother with a slit of any kind. Problem with that is, as you can see here, you disperse it out, so you're getting both the spatial information in this direction as well as all of the wavelength or color information. So everything's stacked on top of each other. So if you were looking here, you wouldn't know whether the feature was from the left-hand portion of this yellow galaxy or the right-hand portion of this blue galaxy. It wouldn't work. So if we did that, we would have no difference between the spatial information and the wavelength information. So that would not be an effective way to look at large things. It is effective for very distant small galaxies, but that's not what I'm trying to study. I'm trying to look at large things. So this long slit spectroscopy is great because it gives us a narrow window into the presence of elements and their movement, but it really does miss the bigger picture. So the instrument I'm building will help us give us this entire picture. So jumping in, I've been saying the entire picture. That's because we call it integral field or entire field spectroscopy. And so similar to long slit spectroscopy, we take the light from the telescope and we focus it. And we don't just focus it onto a mask of some kind, we actually focus it onto a really funny mirror that's called an image slicer mirror array. And it's clearly an array of mirrors because it's actually slices of mirror like this that are tilted slightly with respect to each other. So you've got the image of the galaxy, but you're grabbing this top slice and you're sending it over to a different location in your spectrograph. Then say the center one is sent here and this bottom one is sent over here. So when we do that, we're actually separating slices of the galaxy out and sending it into a different portion so we can handle them all differently, meaning that when we actually look at them and study them, they won't be overlapping on top of each other. So we spread the light out and we send it to some sort of re-imaging lenses because the light focused here and started to disperse again. And then we use that lens to focus it down. And so you can see we reform images of, that top slice of the galaxy, the center piece there, and then, the other end here with that little bit of star showing up. So we basically use it to make a new long slit, in fact, because we're really good at dispersing long slits. So this lets us have the spatial information from each slice without making it super hard to disperse it out. So now that we've got that new slit, we can send it into the spectrograph and have it be dispersed. So then we get the light from all the different portions of the galaxy and can study them separately. But, we spread everything out. We actually have to then rebuild it back into, basically, we'll call it a data cube. It's not just an image like we're used to thinking about with X and Y and brightness per pixel. We have an extra axis now that is the wavelength or the color. So at each wavelength, we can then basically we have a snapshot of that galaxy and its brightness at each wavelength, which lets us do really complicated, cool things. But we have to use software to reassemble it back into the data cube. Optics slice it up and then software puts it back together. So that's the whole picture for integral field spectroscopy. So first, for what I'm building, what telescope are we using? So I'm at Carnegie Observatories. We have access to Las Campanas Observatory, which is down in La Serena, Chile. And so that observatory is made up of 4 telescopes, 2 smaller telescopes over there, and 2 larger telescopes here. I'm using the Bode telescope, one of the Magellan telescopes. And it is actually 21 feet for the diameter of its primary. So that's about 4 of me lying end to end. And as we were talking about briefly before we started, the size of your primary mirror determines the faint object, how faint the objects are that you can see. So having a bigger light bucket is really helpful. And this is a pretty big light bucket, not the biggest, but you know, very high up there on the list. Hopefully my video will play. Yes. So this is the site, and this is the Bode telescope actually observing. The site down there in La Serena, Chile, everyone likes to go to Chile because not just for the fun flight and the delicious food, but because the sky is incredibly clear. There's almost no light pollution. And you can even see the Magellanic clouds over here. So what just happened here, actually, you can see we're still observing, but the sky got bright. That was the moon rising. So that sort of gives you a feeling of how dark the sky is when the moon isn't around at this site. And, you know, we can still see tons of stars. So it's still an incredible sight, even once the moon is up. So this was a pretty great observing night, in fact, because there was no stars or anything, no clouds or anything to get in the way. So then what are we doing on the other end? So to save money, actually, I am not building the whole spectrograph that will disperse the light. A spectrograph already exists. It's a wide field imaging spectrograph called IMAX. It's about as tall here on the end as a person standing. And it's a great spectrograph. The really cool thing, it's got a slot here at the front where I can input something and do all sorts of cool things. I can turn it into an integral field spectrograph by adding my new instrument into it. So if I'm just building this portion of the instrument, that we'll call that an integral field unit, because I'm not building the spectrograph part. I'm just building something to put into the spectrograph and to transform it. So for this particular instrument, its name is the Reformatting Optically Sensitive IMAX Enhancing Integral Field Unit, or the Rosie IFU. And in case you didn't catch it, my name's Rosalie. So, you know, that wasn't at all on purpose. It was a little on purpose. But this is going to be a tremendously cool instrument. So let me tell you more about it. And clearly the only logo we can have is a multicolored rose. That goes without saying. So let me describe what my instrument does in sort of a more schematic way, and then I can jump into the actual details. So the telescope is giving us a field that is not quite the image of the size of the full moon. It's a little stopped down like this. So inside of that whole field that the telescope gives us, we're actually only grabbing a portion that is 30 times smaller than the moon, about, you know, this size. The galaxy is about this size on the sky. So, oh yeah, that's the size of our local galaxies. So then when we take the image that's focused by our telescope, my instrument will immediately chop it into 4 pieces, just optically, using mirrors, basically. So then I will use one of these segments to describe the rest of the things my instrument does to it, but it's happening to all 4 quadrants, I'll say. So when we take that one quadrant, we need to magnify it by a factor of 3, because otherwise it's too small to work with. So then once we have that quadrant magnified, we then chop it into 21 pieces immediately after that. And if we dispersed it just after it was like this, all the light would still be overlapping. So that's not very useful. So once it's chopped into those 21 pieces, we need to demagnify it. So we have to bring the image back to its original size, just like, because the instrument's used to accepting light directly from the telescope. So it would really mess things up if we sent it magnified light. So once we've got these demagnified 21 segments from this first quarter, We then line it up into a long slit. And of course, that doesn't fit on my screen considering the size that they are. So we've got the center here, and then, you know, one there and one there, and then 9 more above and 9 more below, because otherwise it really won't fit. So that's what happens in a cartoon way. This is what actually happens with the optics. So we take the light that's focusing down from the telescope, it goes through an aperture of some kind, and then it focuses onto a set of 4 mirrors, which chop it into that 4 pieces immediately, as I said. So then just grabbing one of those quadrants, the light comes up, it's magnified by this lens, redirected by that mirror, and then it's sent to what we call the image slicer, which is the thing that chops it and fans it into that 21 segments immediately. And unfortunately, we don't have holographic technology yet to show you the best way possible. So when it fans the slices out, what it's actually doing, I'm waving my hands on the camera if you see it, it fans them out into and out of the screen. So some in front of my screen, some behind. So just grabbing the center one to show you what actually happens. So all 21 segments come down here across the instrument. They're demagnified by a second lens. And then we use 2 flat mirrors, fold mirrors, to reposition the light to make it into a slit and send it down into the spectrograph to be dispersed. So I said it happens to all four quadrants. So here's when we take the full light from the telescope. We have 4 mirrors here that divide the field into those 4 quadrants and then deals with them individually. So, and each of them has an image slicer here, here, and here, and here. And they're divided each into 21 segments, meaning we have 4 optical paths after slicing. And then we have 4 slits, as I think I'll show you in the next slide. There, 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 and there. And they will all go down into the spectrograph. So what that means is we're taking each of those 4 subfields and reformatting them into 4 long slits. So this is the size of the original image, and the field of view sent to us by the telescopes about, I'm making a hugging motion. It's about in diameter 2.5 feet. So everything, to fit all of this, everything has to be super compact. So we take this image here in the center, and we've divided it into 4 long slits, because that way we're then able to reformat it onto the camera that will actually register everything. So there are the 4 long slits on the camera. And once we disperse that light, this is what the camera will basically be recording. The light from each of these 4 slits dispersed by wavelength along into sort of this type of pattern. And then we use software again to reassemble that, you know, back into that data cube I was talking about, because we've got all the wavelength information here and all the spatial information along the slit. So to jump into one of the coolest parts, the image slicer is really one of the incredible pieces of technology my boss and I have been working on designing. So it's really, as the original like schematic showed, it's really 21 thin slices of mirror, as you can see here with our prototype, that's set at slightly different angles with respect to its neighboring mirrors. And we're not actually making, and it's also horribly tiny. This is why we had to magnify the beam, because that's a dime. So that is really incredibly small. We didn't think we could manufacture it if it was the original size of the light coming from the telescope. It wouldn't have worked out for us. So we're actually making it out of quartz or glass, basically. So this doesn't actually have the mirror coating on it yet. We've sent it out for that. But this is each one of those mirrors being fanned. You can see the steps better here. So they're each being fanned by 1.5 degrees with respect to their neighboring segments. And they're redirecting that light, you know, as I said, into and out of the screen. Okay, I've been talking about fanning and waving my hands about it. What does it actually look like from the top view as the light fans out? This is what it looks like for one of the quadrants. So we've got the light coming off the image slicer here and sending different, it's actually easier to point this way, sending, you know, the blue beam is 1, the green beam is 2, the red beam is 1/3. So it sends it through that lens, as I said, that demagnifies the light, and then it sends it off to, I made a picture without the incoming beam, one flat mirror, and then a second flat mirror that sends it down, in this case, in this image, into the spectrograph. And so we didn't quite make it a full, like, straight long slit, because it turns out if you take a 2.5-foot piece of metal and you cut 4 long slits into it, like I was originally planning, it has no structural integrity by the time you're done. So it turns out by offsetting the slits by a small amount between each of them, it makes it much easier for us to have an instrument that will be stable. Things you learn as you start designing. Good stuff. Oh yeah, like this. So you can see they're offset, and that's an offset only of about 6 millimeters, or, you know, a tiny portion of an inch. So it's not a big offset. It's still basically the same concept that we're working with. So then after that, so I've been talking about all of these optics here. What will that actually look like? Because everything is pretty small. The second lens here is about the size of my thumbnail. It turns out it's about 1 inch in size. So it's pretty crazy how small the optics are we have to work with. So this is the design. It's no longer preliminary. I should have taken that out, for just 5 of the 21 beams from one quadrant. So we've got, again, the light's coming here as it's been fanned out into and out of the screen. We've got the lens here that demagnifies it. One of our flat mirrors that redirects it. A second flat mirror with sort of a weird shape, because we have to watch the clearance between the beams and the tops of the mirrors. And then it sends that light straight down into basically a little window to prevent dust from getting into the whole instrument, down into the rest of the spectrograph to be dispersed. And so here's what it actually looks like 3D printed. It turns out we were hoping we would be able to 3D print the whole thing with these little dummy mirrors to just, you know, use lasers and understand whether the tolerances would be close enough. But it turns out the 3D printer is coarse enough along the surfaces here that it will not be accurate enough for what we need. So now we're machining everything out of metal. And it will be heavier, but it will be more accurate. And that's what we wanted. So in summary, that's Rosie IFU, with all of our image slicers and, you know, all of the re-imaging everything. So I'm building this cool thing that will get spectroscopy over a large area. What science are we actually able to do with it? Because really, I think that's what you guys care about. So for example, we can study really weird looking galaxies like this one. This is a polar disk galaxy. It's sort of got what we'll call the bulge, which is generally a population of older stars. But normally the bulge is sort of round. It never looks like this. And then it's got a disk of sort of more young stars out here. How is the disk rotating? What happened to cause that happen? So hopefully with spectroscopy like mine, we'll be able to study that. So this is a movie that will move in wavelength. So this will be our galaxy, and it's slowly changing the wavelength here as it goes. And we'll hopefully see the emission lines basically as not a dip, as flashes there. So those were 2 hydrogen and nitrogen lines. And they're showing that the disk galaxy is rotating actually along. So it's still rotating, and it really doesn't seem to have been horribly disturbed or affected by the presence of this particular really weird looking bulge galaxy. So there might be a time delay in whatever caused this affecting everything else in the galaxy. And that's really cool. Without studies like this, we would not know at all what was going on here. So here's another really cool picture of something we could do. So this is an image coming from the Hubble Space Telescope and the Chandra X-ray Telescope. So Hubble gives us this beautiful picture of this galaxy with the red and blue stars in the background, but then we've got this misty blue stuff. So this galaxy is actually falling into a galaxy cluster, which is known to have a lot of, you know, basically hot gas in it. And so what's happening is as this disk galaxy falls into the cluster this way, all of the gas in this galaxy seems to be streaming away from its galaxy. And we can see it in the X-rays because it's really hot gas. But what's incredibly cool by studying this no, come back. By studying it with an integral field unit like I'm building, we're able to see these waves of hydrogen and nitrogen gas even out to these distances. And as this gas is being stripped from its disk galaxy, it's still, even out here, you can see it moving this way, it's maintaining the rotation of its original galaxy. That's incredible. I would never have expected gas that was so far, both in time and space, from its original galaxy to still have the original motion that it started with. So it's still rotating like the galaxy it left. That's totally bananas and awesome. Finally, this galaxy, whatever its phone number is, NGC 1275, has an active black hole in the middle. And so by looking at really narrow wavelength images, we're able to see a really intense, weird structure in the hydrogen gas around the galaxy. But just taking an image of it like this, it doesn't help us determine what the gas is doing. Is it coming into the galaxy, or is it being injected by the galaxy? Are things that are closer moving faster and things that are further moving slower? We really need something like integral field spectroscopy to study that. And indeed enough, when we start moving this cursor through the wavelength, we'll hit our nitrogen and hydrogen lines in a moment, and we'll see it will slow down. Really complex, intense structure of all the lines, and there's even a high velocity hydrogen system, like right there that just went by, very near the original galaxy. So that implies that near the galaxy, there's still high velocity stuff that's being ejected, but that intense structure all the way out to there from the original nitrogen and hydrogen lines, it's really cool. We wouldn't be able to study this otherwise, to try to disentangle what this gas is doing and how it's flowing out from the active black hole there in the center. Unfortunately, though, to bring us back to Earth a little, what we normally study with stuff like this looks a lot more like this. It's not beautiful movies. Of course, when we publish papers, we don't get to show them in beautiful things that move and change, at least until we're in Harry Potter and have moving pictures in our newspapers. So when we study this particular galaxy here, instead of showing it as a movie, we'll show all the light from emission lines out here had a certain velocity, and we'll show it using a color bar with velocities moving away from us in blue and velocities moving towards us in red, meaning that this particular galaxy, this half of it's moving towards us, and this, nope, I just did it backwards. Blue is moving towards us, red is moving away from us. So this side is moving away from us, this side's moving towards us. So the galaxy is rotating as it implies like that, towards and away from us. So this is something we would actually publish in a paper, for example. And we could send people to our websites to look at the beautiful movies, but this is much more what we deal with normally. So in summary, spectroscopy of emission and absorption lines let us find certain elements in their movements, seen, for example, using the Doppler effect. We use long slit spectroscopy to see only part of the picture. An integral field spectroscopy is much more fun just because it shows us the whole picture, like this. And then our integral field spectrograph will open up a whole new avenue of galactic silence on our telescopes, like this, for example. So that's really exciting. So that's what I just went through really quickly. It looks like there's at least one chat question. Thank you so much for your time. Really, Kirsten, I didn't know that. Kristen says in the chat that her mom helped build Chandra X-ray Observatory back when she was in kindergarten. So that's really awesome.
Yeah, she was a software engineer, and for some reason there was lots of news at the time about Hubble. So I told my kindergarten class that she worked in Hubble Space Telescope, and she had to come in and give a whole presentation about Hubble when she had actually worked on Chandra.
Oops.
Wow, that's awesome.
Great job, Rosalie.
Thanks.
Thank you so much, Rosalie. This was super cool. I actually have a quick question.
Yeah, definitely.
Else, but In one of the last images that you showed us, it was kind of the spidery galaxy where the
These
galaxy.
super cool. Yeah.
Did you say that's a black hole?
There's an active black hole in the center of the galaxy. It's what's busy causing all of these really awesome looking filaments to be driven out. It's filaments of hot gas being ejected from the galaxy.
Oh, okay. For my limited knowledge of watching the movie Interstellar, that nothing could escape a black hole, like not even light. So I'm wondering, why would gas be emitted from a black hole?
Yeah, great question. So these are what we'll call supermassive black holes, meaning it's 1,000,000 to 1,000,000,000 times the mass of our sun. And the cool part about, as you said, black holes, the light can't escape if it gets within a certain distance. And so stuff, as it's being eaten, as it's accreting onto the galaxy, as stuff is falling onto the galaxy, it forms generally a disk as it starts to try to like in spiral. But the black holes are really messy eaters, it turns out. They eject some of it in a jet along the polar axis of that spiraling disk. And so what's really weird about this galaxy is it doesn't just have one jet, as I'm waving on my cursor. It seems to eject it in every direction in a really messy manner. We don't understand why, which is one of the reasons why this is so cool to study. Because there could be stars coming in that were, changing the tilt of that disk, for example, as it interacted. But we really have no concept on what time scale that would happen. We don't know, how many stars does it take to spin it, in enough of an angle that we'd see the difference. Stuff like that. So, but because black holes are messy eaters and we can see the stuff that's in spiraling, we can both see the effect when it fails to eat the gas, and as it falls onto the black hole, we can study it. So black holes are so fun.
Awesome. That is super cool. And I love how you personify all the galaxies. It's really cool.
Well, we might as well. I mean,
of course, why not? All right, and if anyone has any questions, please either unmute yourself or input it in the chat and I can read those aloud for you.
I have a question.
Yeah, please, John, go ahead.
Does this technology aid in studying like rotation curves and dark matter?
Yep, definitely.
Studies and stuff like that?
Yeah, so for example, using something like this, we can do modeling of the rotation curve of this galaxy and understand, we can measure the mass based on what we can see in terms of the light coming from the stars and gas. But then, as you say, to measure the dark matter, we need to see how the galaxy is rotating to then model, okay, we know this much mass is visible, but what masses that we can't see is present, the dark matter. So that's what we would be able to see by getting images like this. Because then we'd run a whole bunch of models and then know that, we see X mass and then we see 3X dark matter based on what a model would tell us, for example.
Vera Rubin would be excited.
Yeah, she would be, in fact. I mean, when she was the one who discovered this technique, as you know, but so everyone else knows, it's a really cool way to study galaxies.
I have a question. So the funny thing is, I was going to ask, well, I think what John just asked, but that's because we think alike, except that he asked it like actually knowing what he was asking. So what I was just wondering was, when I'm looking at that picture there, I see how it's like kind of orangish at the top and then red. And so I'm imagining that is, so that's telling me how fast the arm of the, I don't know if that's what you call it, the arm of the galaxy, because I guess orange is even faster.
Even faster.
So when you were talking about that one galaxy that was the
weird polar one.
Yeah, that was yeah, exactly.
Crazy one.
So does the part that's really further out always move faster, or is it sometimes more like a lagging spiral, like where it's like being dragged around like I don't know, if I were to swing a rope around at the edge, it might not go as fast.
That's a good question. So originally people thought that was how spiral galaxies worked. Everyone thought they spun, the outsides moved slower, which is why they looked like spirals. And it turns out, actually, because of how the mass is, there's they actually are always moving faster at the edges pretty much, because the velocity of this, but like, so if you're imagining, you know, a rock and you're swinging that rope around, the longer you make it,
Right.
the faster everything actually ends up going. And that's actually, in fact, it's due to the dark matter and all the mass inside in this case, not, so the rock and the string isn't a good analogy, because as the gas out here is rotating, it's being influenced by everything inside its radius. So the stars here are being pulled by everything inside, you know, its circular radius there. The stars out here are being pulled, spun by all the mass inside that circle,
Right.
which is significantly more mass. So that's exactly one version of Kepler's law that we used to discover exactly that there was dark matter there, because we would have expected, based on the light we see from the galaxy, we would have expected that the velocities out here would drop off based on the mass that we're inferring. And it turns out, based on the far edges of the galaxy, they're moving, they keep moving fast enough that the mass that we see cannot be responsible for moving the galaxy that fast. It has to be the dark matter that's inside that radius.
Cool.
So that's a great question and a great follow-up.
So I guess this tool you've created gives you like a better resolution for the whole galaxy for.
Yeah, because if we wanted to study it with this galaxy, you'd put one slice there, and then but you really would like to know what's going on along the whole thing.
Right.
One long slit picture definitely gives you a starting point, but it turns out our models have gotten crazy more complex than what Vera Rubin used to do. She just did it with a long slit, and it was really groundbreaking and amazing. Now we have 3D asymmetric, either axisymmetric or fully asymmetric models on all three axes to try to understand, because galaxies really aren't, they're sort of symmetric, but they're actually not symmetric as this plot really shows us. Like, there's faster bits in here and out there. Why is that? Similarly, there's, you know, if purple is the fastest, there are some purple bits in here. So you really need a complex model to take into account both the light structure we see as well as the more complex velocity structure. So having all of the information is really critical to then be able to back out what's actually happening with the system.
Thank you. This is really cool.
Great question. I love your background.
Yeah, I'm actually traveling through that galaxy right now.
Makes perfect sense.
Hey, Rosalie.
Yeah.
I got one private message question in the chat.
Yeah, please.
And the question is, do you have any recommendations for a good telescope for backyard viewing with light like you have around in like a city like Santa Cruz that has a population but it's not too crowded?
That's a great question. I am terrible at normal sized telescopes. That's a wonderful question. I would probably go look at some, you know, dedicated magazine like Sky and Telescope, because they generally have really good recommendations. I know Meade, for example, MEADE, sells great telescopes. And if you got something like an 8-inch or a 10-inch, that would be amazing to start both doing just eyepiece observing, you know, looking through and seeing things. And then if you wanted to start viewing more, that telescope would be a really good way to like move into that.
Awesome. These are great recommendations. Thank you.
Yeah.
There's also Orion telescopes is sort of.
Yeah, that's right. Orion telescopes is another one.
Yeah, they're great for talking to people, and they're friendly and great people and stuff.
Yeah, so picking a company that like actually is willing to work with you is a great a great plan. Windows. Anybody else? Because I'm happy to answer both questions about this and like generally, as I've shown. I like talking.
No, I had no idea.
Thanks. Yeah, I know. That's a surprise to you.
I ended up joining late, but I hope you mentioned earlier on that You were a wise officer back when you were at Santa Cruz.
So were you.
Yep. Yeah, it's fun to see WISE and Science on Tap continuing since we helped start it.
It is.
Not quite as much fun as being at a bar drinking and eating while we listen, but
No.
it's nice to have to leave
It's
home.
warmer.
Warmer, easier to record.
Yeah, that was always a mess recording at the
Yep.
bar. Yeah.
I can hear way better.
It's true, right?
Yes, and Rosalie can join from Pasadena and I can join from LA. It's great. Anyway.
So are you going to be making more like videos showing velocity distributions? I can't think, not
So
curve,
we
but
do intend to,
movement.
for our instrument, we do intend to have something that will help make movies like this.
Mhm.
One of the telescopes that's currently already doing it, a bunch of these videos were from man, did I not put a credit on here? So it's this link down here. This person is making a whole bunch of movies from one of the European telescopes. They have a whole bunch of, they're 8 meters, so that would be like 26 feet diameter. So they've got this really cool instrument called Muse. It's an integral field spectrograph like mine with a pretty big view like mine. And it's one of like only a few instruments that can do this. So this person is out there making these really fantastic videos of these different galaxies spinning, basically. And not very many people are making videos, which is really horrible because talking about stuff like this, you really don't want to show someone this color map to start. You really want to show them a movie.
Yeah, I was a little surprised when you said that. 'Cause these days, most journals are online, so I would think you probably could embed a video, actually.
Yeah, it turns out a lot of the software we use, it's not quite so easy to make smooth videos or to get the color scale to work on every step of the video. So I think it takes enough fine tuning that many astronomers don't appear to want to bother, which is silly and a terrible idea because then you don't have anything to show when you talk about it. There are 2 things in the chat. Ah, someone typed it up. Yep. It's definitely that one.
Thank you for sending those links.
Anybody
I
else?
figured if I'm typing it up, I might as well share it.
Yeah, he's just got a whole bunch of videos. So I cherry picked up a couple of my favorite, but you know, I really appreciate it when they have, there's another one. This one is from, their specific website from the Very Large Telescope. The Europeans are not very creative in naming their telescopes. The Very Large Telescopes is a VLT, nicely done acronym. But
All right, do we have any more questions for Rosalie?
Thank you so much.
Thank you.
thanks so much for spending your evening with me. I appreciate it.
Thank you so much, Rosalie. This was awesome. And this was recorded, so we will be able to put this on our YouTube channel for people that
That
Good
will be
night.
night.